It's really exciting to see the power of the JWST telescope, specifically testing these abilities on a specific planet. And based on this article, it is incredible to see that yes, JWST telescope is able to detect the temperature of a planet. And yes, it is an exoplanet, and this exoplanet is truly special because it is a rocky exoplanet. It is known as TRAPPIST1-b, which is located at the TRAPPIST-1 region, one of many exoplanets that are a really incredible sight for astronomers to experience. Why is that the case? We're going to look at how this technique was enhanced using the JWST telescope, how this is compared to other telescopes in terms of why it is quite difficult to detect temperature, and thirdly is how is this going to change our understanding of understanding planets as with regards to harnessing or fostering life on those rocky exoplanet. So let's begin. Now, looking deep at the illustration, it says here that the illustration shows what the hot rocky exoplanet TRAPPIST1-b could look like based on this work. Now, the TRAPPIST1-b, the innermost of the 7 known planets in the TRAPPIST-1 system, orbits its star at a distance of 0.011 AU, completing one circuit in just 1.51 Earth days. Now, the TRAPPIST1-b is slightly larger than Earth, but has around the same density, which indicates that it must have a rocky composition. Now, the Webb's measurement of the mid-infrared light given off by TRAPPIST1-b shows that the planet does not have any substantial atmosphere. The star TRAPPIST-1 is an ultra-cool red dwarf, M-dwarf as it's called, with a temperature of only 2,566 kelvins and a mass of just 0.09 times the mass of our Sun. Now, this illustration is based on new data gathered by James Webb Mid-Infrared Instrument (MIRI), well as previous observations from other ground and space-based telescopes. Now, Webb has not captured any image of this planet yet, so that is something definitely to look forward to in the future. Now, looking at the data about the day side temperature comparison of the TRAPPIST1-b exoplanet, it says here that this graphic compares the day side temperature of the TRAPPIST1-b as measured using the Webb Mid-Infrared Instrument to computer models of what the temperature would be under various conditions. Now, the models takes into account known properties of the system, including the temperature of the star and the planet's orbital distance. Now, the temperature of the day side of Mercury is also shown for reference alongside that of Earth, as you see in here. Now, the bright side brightness of TRAPPIST1-b at 15 microns corresponds to a temperature of about 500 kelvins, as roughly around 450 degrees Fahrenheit. Now, this is consistent with the temperature assuming the planet is tilted, locked, and one side is facing the star at all times. Now, with a dark colored surface, no atmosphere, and no redistribution of heat from the day side to the night side. Now, if the heat energy from the star were distributed evenly around the star, for example, by a circulating carbon dioxide and free atmosphere, the temperature at 15 microns would be 400 kelvins, which is around 260 degrees Fahrenheit. If the temperature had a substantial amount of carbon dioxide, it would emit even less, which is 15 microns light, and would appear to be even cooler. Now, although TRAPPIST1-b is hot by Earth standard, it is cooler than the day side of Mercury, which consists of a bare rock and no significant atmosphere. Now, Mercury receives about 1.6 times more energy from the Sun than TRAPPIST1-b does from its own star. Now, in addition to all those information, it states here that the James Webb Telescope is able to detect the infrared rays that is coming off from the planet in terms of the planet's thermal emission process, and therefore this actually reveals some stunning results that in conclusion that this planet doesn't have an atmosphere, that is one, and two, the daylight temperature is around 500 kelvins, which is close to 450 degrees Fahrenheit, which is astonishing here. Now you might be wondering, when was this particular region, which is TRAPPIST-1, discovered? This was discovered around 2017 when astronomers discovered this particular 7 in number, and these 7 planets are orbiting around a red dwarf. Now this particular red dwarf star is ultra cool in nature, and looking at the distance from this particular TRAPPIST-1 to Earth, it is around 40 light years away, which is really close. In addition to that, when you're thinking about the 7 rocky planets that are orbiting around this cool ultra cool red dwarf, it is incredible to see how all those 7 can fit within the orbit, like for example Mercury's relative to its own sun. So therefore it's really fantastic to receive that much balance in energy relative from one rocky planet to the next, and this is really fine for astronomers to really understand really deep about that particular different solar system, of course different from ours, but still have a comparable similarities with how they orbit and their structures of those rocky planets in terms of the mass relative to that of Earth. Now, for comparison of TRAPPIST1-b to Earth, it is known that TRAPPIST1-b is one of the innermost planets in that particular TRAPPIST-1 zone, and this is really important because it is known to have a radius or orbiting path that is 1/100th that of Earth, and in addition to that it gets 4 times more sunlight than Earth receives from its sun, and therefore this here is not really a convincing way to say that this planet is going to be one of those planets that is at the habit zone region or habitable region in that particular space. Therefore we might actually see insight, hopefully, as to how other planets or rocky sized planets in that particular zone may be at the habitable zones, and that might be a great analysis for future astronomers or future data to come in. And the final data here focuses on the light curve, which says that this light curve shows the change in brightness of the TRAPPIST-1 system as the innermost planet, the TRAPPIST-1-b, moves behind the star. This phenomenon is known as a secondary eclipse. Astronomers use Webb's mid-infrared instrument to measure the brightness of mid-infrared light. When the planet is beside the star, the light emitted by both the star and the day side of the planet reach the telescope, and the system appears brighter. When the planet is behind the star, the light emitted by the planet is blocked, and only the starlight reaches the telescope. Now this causing the apparent brightness to decrease. Astronomers can subtract the brightness of the star from the combined brightness of the star and planet to calculate how much infrared light is coming from the planet's day side. This is then used to calculate the day side temperature. The graph shows combined data from 5 separate observations made using the MIRI's F1500W filter, which only allows light with wavelength ranging from 13.5 to 16.6 microns to pass through to the detector. The blue squares are individual brightness measurements. The red circles show measurements that are averaged to make it easier to see the change over time. The decrease in brightness during the secondary eclipse is less than 0.1%. MIRI was able to detect changes as small as 0.027% or 1 part in 3,700. This is the first thermal emission observation of TRAPPIST1-b, or any planet as small as Earth and as cool as the rocky planets in our solar system. The observation have been repeated using a 12.8 micron filter in order to confirm the results and narrow down the interpretations. In conclusion, this is astonishing to see the different techniques in order for them to determine the temperature of this planet and the atmosphere as well of this planet just by James Webb Telescope's mid-infrared region, and how this is going to enhance the understanding of other planets that are a little bit outside of the orbit of this zone, which is the TRAPPIST-1 region. So really fascinating to see the future of this particular space, which is pretty much 40 light years away from Earth, and how this can be something that we can observe and how that might impact our own understanding of our relationship with our sun, as maybe our sun will be heading towards that particular type of the star, which is the red dwarf. So let's know about your thoughts about this in the comment section down below. By that way, I can talk to you soon. Stay smart as always and believe in yourselves.